So that gets us, a picture or one sample from one depth in one point in space. And you can imagine that there's a whole slew of problems that come with collecting data that way. But that's historically how things have been collected. Again, that gets us, there we go, soil samples, and we can test those in the lab. But again, this is just representing one point in space. Geotechs have also historically relied on geologic maps, which are two-dimensional geospatial. But in the last few decades, we've been adding dimensions and therefore adding lots of data to geotechnical engineering. So another really common way to collect soil information is with something called a cone penetrometer test. All you need to know is that gives a one-dimensional profile of engineering parameters from the surface to the depth at which you advance, and it's a continuous profile. So it's like a one-dimensional data set. That's what we're going to be looking at a lot today. Expanding beyond that into 2 dimensions, we can collect geospatial information with drones, and we're still using a lot of maps. You can also make 2D profiles with geophysical things. So you can see how things are getting more complicated. And again, with drones and other technology, we can capture things, geotechnical information, in 3 and 4 dimensions, the 4th dimension being time, how things change over time. So what's happening is geotechnical engineering is transitioning from a data poor to a data rich field. And in doing that, we still have the same objective to characterize subsurface conditions, but we have a lot more information to do that, and that brings opportunity and challenges. So there's been an increased need and an increased adoption of data science tools, and then AI and machine learning to sort of accommodate these growing data types. And the trend is clear in the literature. So I'm going to share a literature review that my advisor and I did last year on AI and machine learning in geotechnical engineering. And we just looked at one really small corner of geotechnical engineering, right? Because I'm a PhD student, so the scope of my work keeps getting narrower and narrower, and so I'm working it down. And that corner is soil liquefaction, and we'll talk about what that means. But all you need to know right now is that's one problem in geotechnical engineering. And so we looked at how the literature is looking at this soil liquefaction problem using AI and machine learning. And we reviewed 75 papers, which was just a subsample. It was not a comprehensive review. And as you can imagine, or as is shown in this figure, even those randomly selected papers, we see a sort of general increase in papers published in the last few years. So we think that this is really exploding. But something I want to highlight is that these papers were from leading journals in our field, and that will become relevant when you see some of the issues that we found in these papers. So what prompted us to write this paper was noticing that there's this growth of models that people are using to describe soil liquefaction, but we didn't know of anyone in practice that was using these models. None of the papers were necessarily referencing other papers. It didn't seem to be a building effort. It seemed to be in isolation. And so we were wondering, why are practitioners and researchers alike ignoring these models? So in this figure, we have the state of practice models, we call them. These are essentially the ones that everyone uses in engineering practice. These are the bars and the number of citations per year. We normalize them per year because some of these are quite old, that these state of practice publications get. And then these are the papers that we reviewed. So you can see most of them had almost no citations and were largely being ignored. So we were curious why. We identified a few reasons for that. And so first, we realized that generally these models, again, are not compared to state of practice models. They depart from the best practices in model development. They use AI in ways that may not be useful, are presented in some ways that overstate complexity, and that the models are discussed but are never provided, or not actually provided oftentimes. And so I'm going to go through examples of each of these, but we made this Sankey diagram to illustrate that thick band that you see at the top. That represents essentially 50% of the papers felt like more or less the same paper. They used a neural network to model just one type of soil liquefaction. And they did not compare against other models, and they did not provide the model. And I felt like I was just reading that same paper over and over again with small changes. So to dig a little bit more into each of these, the first why, models are generally not compared to state of practice models. Again, about 2/3 of the models had no mention of anything that's presently used in practice. An example of one paper that did compare it to practice, they said, this rate of successful prediction, talking about their own model, is about the same or a little higher than those normally achieved by traditional methods used in practice. So sort of a loose comparison there. I don't know if I would actually call that comparing to the state of practice model. One paper did self-cite, and they republished their paper when they had achieved 1% higher accuracy in liquefaction prediction. We asked, why should a reader want to use a new model that hasn't been shown to outperform an existing model? Geotechs are notoriously a bit conservative, and so you don't want to use something that you're not comfortable with. Okay, the second thing, models generally departing from best practices in development. These are really small data sets that these models are trained on. Part of that is not their fault, right? We're predicting something that's an earthquake, result of earthquakes, and there aren't a lot of large earthquakes that happen every year. There are some, but it's not an everyday occurrence, and so the data sets are small. And then sometimes data sets are really big, and you think, well, there aren't that many large earthquakes, so how do you have 10,000 points? These data sets are often unbalanced, so maybe often liquefaction was treated as a binary, so yes, liquefied, no, did not liquefy, and maybe 90% of the data set would be yes, and 10% would be no, and so you can imagine how that might bias an AI model. Statistical analysis was largely limited to overall accuracy. So in that case that I just gave, in an unbalanced data set, if your model learns to predict liquefaction 100% of the time, then you have a 90% overall accuracy, and you're doing pretty well. You're doing better than standard practice model there. So on paper, it can look okay to a reviewer that might not know what they're looking at, but there's some really bad problems there. And oftentimes there's indications of overfitting. So we saw reported accuracies commonly of 99 or 100%. And that just doesn't make sense. Like the mechanics that we've been developing for 50 years can predict about 70 to 85%, which we think is pretty good. So yeah, that was a red flag. Okay. Some uses of AI that may not be useful. So about 13% of the papers that we looked at, that should say bivariate regression, sorry about that, used AI to essentially redraw this boundary line between liquefaction and no liquefaction, which is arguably, not a necessary use case for AI. They would predict the predictions of mechanical models. So I don't understand necessarily the use case for that. If you could use the mechanical model, or you could use an AI that predicts the predictions of a mechanical model, why you wouldn't just use a mechanical model? But that was something we saw quite a bit. Again, repeat modeling and others. So kind of going back to that Sankey diagram, I felt like I was reading the same paper over and over again. And so the fourth thing was that models are generally presented with overstated complexity. We call this the woo-woo effect. So one example, and I've read the sentence so many times, and I still don't understand what it means, but one model said that they were a hybrid model using an imperialistic competitive meta-heuristic algorithm incorporated with multi-objective generalized feed-forward neural networks for the purpose of liquefaction potential analysis. Again, as a geotechnical engineer who's not really sure what all that means, I might move on and just use something that I'm more comfortable with. So understanding your audience, I'm not saying that sentence is wrong, but just understanding your audience and who you want your user to be when you're describing your complexity. We encountered algorithms that self-described as being inspired by honeybee swarms, fireflies, ant colonies. This is a personal favorite, the predatory instincts of antlion larvae. adaptive resonance theory, and the hunting behavior of gray wolf packs. And it just, yeah, a bit confusing. So the thing that I want you to take away from this is that AI liquefaction models will not be used by geotechnical engineers unless they're convinced of their benefit and it's clear what they're doing. So this woo-woo effect can disguise that. And finally, and maybe most simply, a lot of times these models were discussed but not actually provided. So of the 75 papers we reviewed, only 10 of the papers actually provided the trained AI model for you to use on your own data, which is a crazy concept. If you think about deriving another empirical equation, writing a paper about this empirical equation that you derived that has 99% accuracy and then never giving the equation. I don't know if that would fly in a lot of places, but yeah, so that was a big problem. 3% said that they were available on request, and I requested with no success. So that's maybe the most glaring issue. This assessment was well received, and I've got a link to this paper. It's at the end too, if you're curious in reading it. So the journal was appreciative of the paper, and I think there's a need for education and review frameworks. Like peer reviewers may not have knowledge of these sorts of things, and if it sounds novel, then they may be inclined to accept it. And so it's our responsibility, I think, to educate each other and to establish these review frameworks and best practices in our own disciplines. So we try to bring these lessons into our own liquefaction modeling, comparing to state of practice models, utilizing best practices, employing AI in ways that are useful, being clear in remembering our audience, and providing the needed codes and models. And so I'll ask all of you if this resonates with you, or if you could imagine a similar exercise in your own discipline, it might be worthwhile. Okay, water break. So now I'm getting into the meat of my presentation. This is sort of like when I was making this, I felt like I was making Dune Part 1, where it's just like all exposition. And we've got a little bit more exposition, but then we're going to get to the sandworms and stuff. Okay. So I use what's called mechanics-informed geospatial machine learning. And the methods could be applied to many different natural hazards, but my focus is earthquake-induced hazards, and particularly earthquake-induced soil liquefaction. So a little bit about what soil liquefaction is for those who don't know. It's a phenomenon when loose saturated sand is subjected to an earthquake load, so shaking. The particles of sand become suspended in the water, and the fluid, it becomes a viscous fluid, essentially. It loses its strength, and that causes many different issues. So I call these sloshing sands, saturated loose sands that are shaking. So if you were one of the kids in your youth that you thought quicksand was going to be like a big problem in your daily life because it was always brought up in cartoons, but now you haven't thought about it since, today's the day. I think about it every day. So sloshing particles, as I said, liquefied soils behave almost like a viscous fluid in a lot of ways. And so what happens is things that are less dense in that fluid float, right? Water mains, gas lines, that can cause stress on those gas lines. They can break, start fires and other things. Things more dense in that fluid sink, i.e. buildings and cars. So it's a very disastrous phenomenon. The data that we're going to look at today is from the 2010-2011 earthquake sequence in Christchurch, New Zealand. And that's what this car picture is from. And that caused $45 billion in damage in the city of Christchurch. It can just be monumental. So big problem. And when we go to predict liquefaction in engineering practice, we're pretty good at it. As I said, 70 to 85%. And that's at the site scale, right? So for a building or maybe a bridge, we've got the mechanics established over the last 50 years that we feel okay about taking like a one-dimensional CPT profile, like we were talking about before, taking that profile and computing the liquefaction hazard for that and extrapolating that to the bounds of a site, something that we feel pretty good about. But at the regional scale, like trying to predict what happened in Christchurch, we can't use those same methods. We can't do a CPT on a grid style across an entire city or country as much as I'd like to. We can't do that. So this is where geospatial liquefaction modeling comes in. It's trying to understand these hazards at regional scale. So, you know, we could predict how this whole city of Seattle, what the probability of liquefaction may be from an earthquake in Seattle, those sorts of things. And the ability to do something like this would have far-reaching implications, right? We could use it for urban planning, understanding like what schools and hospitals are most at risk in a given event. If you're a utility or a transportation network, understanding what roadways would be most affected, what assets. We could use it to predict like the safest, if you will, emergency response or evacuation route following an earthquake from a liquefaction standpoint. So it sort of unlocks these insights beyond conventional practice right now. Liquefaction is an earthquake-induced phenomena, or earthquake-specific, excuse me. So from one earthquake to the next, whether if we're in Seattle, if an earthquake starts on the Seattle fault in downtown, or if an earthquake ruptures on the interslab or in the subduction zone, like all of those look different from a liquefaction standpoint and have different implications. And so the tool that we're making has to be earthquake specific. Here's an example from Christchurch. This is our model that we'll be going through today, but the probability of ground failure from one event to the next, these scales are the same. You can see how that changes. And so for geotechnical engineers and some others in this field, there's a tool called USGS Shake Map, and I'm going to try to hop onto my slideshow here for a second. Some may be familiar with this tool, but it's an earthquake catalog, and you can, search recent earthquakes that happened, and sometimes they're available within minutes, which is where we think our tool could be useful for emergency response, right? An earthquake is available, motion is available within minutes, plug it into our model, and then predict emergency response and evacuation routes. There's also scenario earthquakes in this database and historic earthquakes, so you can evaluate your region for a hypothetical event or back check it against an event that has already happened. So all that's available in this Shake Map tool. And I'm getting ahead of myself, but eventually we imagine our model built into this as just another tab in this tool. So these Shake Map earthquakes are the input for our model. And the last thing that we need is for this model to extend beyond one region, right? Seismic hazards are not just in Washington, they're not just in the Western US, and they're not just in the US in general. It's a global thing. So essentially the goal of our project is to advance geospatial liquefaction modeling on a global scale. We're trying to make a global model using geotechnical and geospatial data, AI, and mechanics. And ultimately, we hope to produce a model that can predict probability of ground failure quickly at high resolution, right, on the scale of a building or an individual asset, and at regional scale across the whole area that could be affected by an earthquake. So the work I'm presenting today is for a proof of concept model that we did in New Zealand. And I'm currently working on scaling this model development framework up to the world. It takes a little bit more computing power and some additional tools, but so I'm just going to share the New Zealand work today. And the data set for this New Zealand work came from that 2010-2011 earthquake series that I was talking about. After that earthquake, the country of New Zealand did a massive investigation across the whole country because it's sort of interesting, but the government there insures everybody. And so the government was on the hook after the earthquake for the damages to people's homes and things. And so there was a motivation to mitigate this this scale of event from happening again. So New Zealand has 16,000 CPTs. For scale, the model that I'm building in the US we have 1,500 right now, and we feel pretty good about that. So this is a lot of data for one country. And a CPT, again, is a one-dimensional profile that gives us engineering parameters with depth. And that's sort of all I'm going to get into there. And yes, this dense sampling is in the Christchurch region from those 2010, 2011 earthquakes. And as I mentioned, we believe this can be expanded globally, and I'm working on that right now. So the first thing we do to build our geospatial machine learning model is we compile geospatial predictors that we think might indicate soil liquefiable soils present at a given site. So this is, we're collecting any maps that essentially satisfy the sloshing, right? So if a predictive variable that may indicate whether or not there's sands, if the sands are loose, etc. So we came up with this list, and this is an abbreviated list. We have more than 50 geospatial variables, but the ones bolded and italicized are the ones that were determined by our model to be most important, and those pass the gut check, if you will. So, you know, slope and distance to river, geologic unit, groundwater depth, and VS30, which is like a density proxy. And so this is what one of those geospatial predictive variables might look like, right? It's a mapped parameter. And what we do is we go to each of those 16,000 locations that we have a CPT, and we sample all of our predictor variables at that location. And that becomes our feature data set. One thing that we're kind of curious about from a best practices standpoint is how our training data represents the predictions that we're going to try to make. So we're eventually going to try to predict these for the whole globe. How does the training data that we have represent the predictive variables that we'll be using for the whole globe? So which is something that we're looking at along the way. Okay, so we have our feature data set, all geospatial predictive variables. The target variables, this is a supervised machine learning model that we're doing. The target variables, we call those mechanics-informed target variables, which is where we get the mechanics-informed geospatial machine learning. So this is, I'm trying to brush over the engineering mechanics as much as possible here, because it's not really important. But so all we need to know is that something called liquefaction potential index, LPI is what I'm going to call it. It's computed for a given CPT for a given earthquake, because remember, liquefaction potential is an earthquake-specific phenomenon. So what we do is we compute this LPI for a bunch of different earthquakes across the range of what's physically feasible, and we fit that with a curve. We call that a manifestation curve. So you can imagine, can you see my pointer? No. You can imagine that the actual computed LPIs are sort of distributed around that line, and we fit them with a curve. And we describe that curve with this functional form, which is kind of gross, but all that we need to know is that, of course, it depends on PGA, which is the X variable. That's great. And then there's two curve fitting parameters, A and B. So essentially, we can predict, we can describe the liquefaction response behavior at any CPT location with just two scalar values. So we kind of boil down engineering mechanics into two scalar variables that we can predict in a supervised machine learning model. So now we've got our training data set. We've got our mechanics-informed targets, got our geospatial predictors, and we're going to train an AI model to predict the liquefaction response, the mechanics-informed targets from the geospatial predictors. And so we're playing with several different model architectures for this New Zealand model, and we're evaluating them on several different performance criteria, looking for overfitting and bias, variance, these sorts of things, and then also performance and accuracy. And ultimately we decided on a really complex bagged ensemble tree model, and we split it with a 90-10 data split, used tenfold cross-validation to try to again mitigate overfitting, and we tuned hyperparameters for each A and B parameter so that we have actually two separately trained models, one to predict A and one to predict B. So once we have that trained model, then we can go sample our geospatial predictors at every location across the country at a given resolution. So we selected a resolution of 100 meters. So we predicted liquefaction response then at a resolution of 100 meters across the whole country. And then the last and key step that we did here is anchor the predictions to known CPTs using something called regression kriging. We computed at known CPT locations, we computed the residual between what the AI model thought based on the geospatial predictors, what the AI model thought the A and B should be, and what it really was computed from the CPT. And then we sort of extrapolated, or not, that's not the right word. That residual degrades with distance from the point. I'm struggling to describe that, but essentially what happens is in the vicinity of geotechnical data, the geotechnical data, the mechanics rules, it's giving the predictions, and then distal to geotechnical data, the predictions are based on AI. And so the idea is that in city centers and things, this data is more dense, and a company or an authority could use their own data to further krig this, further improve their model. So that's sort of our final step. And we have, again, these final maps of A and B that are ready for use. So for our model use workflow, the model products are just those two rasters. So the end user doesn't have to do any AI predictions themselves. They don't have to do any sampling of geospatial predictors. All they need to do is a couple raster calculations, which can be done in ArcGIS, Python, MATLAB, or could easily be built into USGS or ShakeMap. So for any earthquake ground motion, like the one shown here, this is just an example. You sample the A and B at those exact locations of your PGA map. You plug them back into that ICHI equation and perform a raster calculation. There's a quick transform that I'm really going to gloss over to get from LPI to probability of ground failure. And so what you have at the end is a probability of ground failure map due to liquefaction for that specific event. And this can be repeated ad nauseum. So, sticking to our best practices here, we compared this to the state of practice geospatial liquefaction model, which is currently built into ShakeMap, and that's the Rashidian and Bayes model. So that's shown at the top here. The scales for all of these maps are the same, and I'll note, yeah, you can kind of see. Okay, so the white dots are where liquefaction was observed in this particular earthquake that was used to make this map, and a black dot is where liquefaction was not observed. So this first map is the current state of practice, Rashidian and Bayes. You can see, they were predicting 40 to 60% in the vicinity of a lot of liquefiable material. They sort of missed what was out here. This is just like on a neighborhood scale. They missed what was out here and some of this. This is our AI model before we did the kriging. And so, there's 20 to 40% in this area. It does okay. And then after kriging, right, on that neighborhood scale is where we really start to dial in on our model. And we also compared our model to the Rashidian and Bayes model using receiver operating characteristic curves and area under the curve analyses. And I feel like on this neighborhood scale, like it looks like our model isn't doing as well. But on the wholesale of our entire case history data set, our models significantly outperformed the Rashidian and Bayes model. And this blue line here is our model, and that's before kriging, because we can't do this ROC analysis after kriging because the case history data is what we use to do our regression kriging, so it wouldn't be a fair comparison. But from an AI model to AI model, one-to-one comparison, our model does significantly better. Okay, so to summarize, I'm going way faster right now than I did when I was practicing. Okay, That's okay. We'll get you out of here early today. So in summary, the AI model is trained on and anchored to like real test data and guided by liquefaction mechanics. It allows for a large quantity of predictor variables. I think I said 50. Our global model is going to have 50. This is 30, allowing us to exploit that information. Our model exhibits an approximately plus or minus 10% mean absolute error and probability of ground failure, which that is some like a number that I can kind of grasp, right? So at any given location, our model gives you about plus or minus 10% of what the probability of ground failure is for any given event. This workflow allows the user to predict possible liquefaction impacts quickly at map scale at about 100-meter resolution. I'm not going to talk about the 20-meter stuff right now, but for any earthquake event. And this model significantly outperforms the leading model according to available case histories. And we think there are a lot of exciting use cases for this sort of model, which is something we're hoping to do next. And again, simple modeling framework that someone could easily perform using existing tools. You don't need high performance computing or anything like that. Or it could be readily packaged into USGS or another software. And just to back check ourselves, coming back to the beginning of the presentation, did we follow our own best practices? So we compared to state of practice models, check. Utilized best practices in model development to the best of our abilities, check. Employed AI in ways that are useful. I think so. Maybe that's a bit arbitrary. We did our best to remember our audience in our communication, and we provide the needed model. So with that, thank you very much. I put my GitHub up here because I think almost everyone does that. There's nothing on my GitHub yet, you guys, but there will be. Once this project is over, it'll definitely be posted there. So if you're interested, follow now and you'll see later. Thank you.
That's great. Thank you, Morgan.
Yeah, thank you. Any questions? Yes.
Hi, I was wondering if we have AI models on like fluid dynamics, using the field, are using models inspired by like insect swarms, which like I think is really cool, but I don't feel like this is really stuff when we have so why are we using models that are more specialized for
That was our question too. That's a really good question. And not to say that that person's approach wasn't appropriate. I don't know. Like perhaps they looked at several different ways and this was like the best architecture for them. But it was like the way in which they described it that sort of lost the reader to all of a sudden be reading about gray wolf hunting behavior. So that was sort of our point, but that's a good question. Yeah.
I was curious, like, what can we really do with this data in terms of like, can it inform like building codes? Or
Yeah.
are there mitigation strategies?
That's a really good question. Thank you. So yes, hopefully inform mitigation strategies. That's like kind of our key goal is that transportation authorities like WSDOT and SDOT and other authorities that maintain a lot of infrastructure that they will use this to evaluate, perform vulnerability assessments and identify what their vulnerable structures are for mitigation. We also, are curious about how it might align with like demographic and population information, like identifying areas that are most likely to be affected, like in Seattle, SOTO. I don't need to run the model, tell you SOTO, but that it can help, inform some of that. And we're working with the structures group, structural engineering group in civil department they're doing a similar, vulnerability assessment of bridges. And so we're trying to integrate like we're looking at the vulnerability of roadways that gets you all the way to the bridge abutment. And then they're looking at the vulnerability of that bridge. And so can we use those together to inform better evacuation routes and those sorts of things? Yeah. Well, girl.
Oh, go ahead.
I'm curious, like, you mentioned that there's like some best practices that people sometimes depart from, like
Mhm.
with the unbalanced data set or it's too small.
Yeah.
I think that people should like refrain from using these models on such data sets. I guess I'm envisioning a situation which like there's no problems with the data set, but it would still be like useful to try to make predictions. And do you think it's like important to make caveats, or do you think it's actually like misleading to create these models on the data sets, or just using the wrong method?
That's a good question. I think being upfront about your data set and like acknowledging the limitation to some degree, like an unbalanced data set is hard to avoid. Like the case history databases are inherently unbalanced, but identifying that and then trying to maybe do some sort of like different sampling techniques or other overfitting mechanisms to identify like if the unbalanced data set is affecting your predictions, and also using other statistical methods other than just overall accuracy to like see how your model's doing and seeing if that unbalanced training data is being transformed into unbalanced predictions. Yeah.
Thanks, it's great. I'm wondering, to talk more about like how you did your train test split, and was that like random on a point by point basis, or was there some like consideration of like correlation between the different points?
Yeah, so we used a tenfold cross validation there too, which is like often built into a machine learning library where you can specify that the split distributions of predictors are like as similar as possible, so that you're not subsampling. You're not like entirely missing one whole class. Let's say if you have a classifier variable, that you're not missing that whole class in your training data and then trying to test on it. So it helps with those distributions. Yeah.
I guess my question would be a follow-up maybe on this. It's have you tried your model outside New Zealand? Like how what are the next steps really to further like test this model to see if it's transferable to other conditions, to other continents? I don't know.
Yeah, really good question. So New Zealand is so interesting because it has so much data, like everything from an earthquake liquefaction hazard perspective, like mechanics wise. If you're in New Zealand, you have your own New Zealand specific mechanical framework, and then outside of New Zealand there's like a global mechanical framework. So we're not using right now this New Zealand model to apply globally, but we're retraining a global model. So we're using the New Zealand data as well as like 30,000 other CPTs from across the world, and training that to make an entirely new model. And then that new model will test on like any global earthquake. So we can test on Northridge and earthquakes in Japan and those sorts of things. So yeah.
Well, good luck with that.
Thank you. Yeah, thanks.
If there's no other questions, we're gonna wrap our seminars here today, and I'll invite you to join our seminars next quarter. We have a room, Lisa, I think.
We do. We're back in the physics and astronomy auditorium building.
You know where that is, and yeah, sign up for the seminars to give one or to attend one, and good luck on your exams.